first lesson of our new topic, rate of reaction. For this first lesson, I've got 3 questions as a knowledge quiz for you to have a go at. So pause the video, give yourself about 5 minutes to see how many questions you can answer, and then I will go through the answers in a moment. So these are the answers. A few that I like to pick up on is just a reminder about lime water. So lime water solution is calcium hydroxide. And so the reason why it turns cloudy is that this calcium hydroxide reacts with the carbon dioxide and forms calcium carbonate, which is a solid. And so the reason for this cloudiness is that it is a white precipitate, so PPT precipitate, that is formed. Reason for our squeaky pop is because it's such a high energy releasing reaction. That's why it gives that squeaky pop. Chlorine, the turning white, we say that the ions bleach the paper. And of course, this idea that a struggling fire needs oxygen in able to relight is part of that fire triangle. So these are some of the other ways that we can recognise that a reaction has happened. So bubbles of gas, when gases are produced, that indicates to us something is going on. Colour change, whether it's a precipitate that forms as well, that can be an indicator if it was a solution to start with. We can also have colour changes of solutions as well as coloured solids formed. We can also have an energy change, which we can have an indicator from temperature, so whether energy is taken in or released to the surroundings, which you will have looked at last year. And question 3 links in to that topic that you'll have looked at last year. So this is for our exothermic reaction. Overall, we have an energy loss from our reactants to our products, and so because we've decreased energy going from reactants to products, that gets released to the surroundings, and therefore we have an increase in temperature. So for this lesson, I've prepared a worksheet that will accompany the rest of this lesson that you can fill in as we go through the video. So the first thing I would like you to do is to think about how you would determine the rate of cooking an egg. So pause the video while you have a think. So when we think about rates, we think about how quickly things are happening. And so when we are cooking an egg, we measure the time that it takes for that product to form. So we know the egg is cooked when we see the white and the solid formed compared to that transparent liquid that it starts off with. So thinking about how quickly that happens, we can measure our time and have a look at how quickly that has happened, whether it's taken a long or a short time. How about popcorn? Again, pause the video, have a think about this. So with popcorn, we look at how long it takes for all of the reactant to have gone. So for all of those popcorn kernels to have popped. So again, thinking about the rate, so how quickly all those popcorn kernels will pop. And we can apply this to our rate of reaction. So our rate of reaction is the rate at which what are used up, or the rate at which what are made. So pause the video, write down what you think goes in those gaps. And now with a different colour pen, you can fill in reactants and then products. And we can use this and make this into an equation. So we can have 2 equations here. It's been written as one here, but I will write it up top so that you can see how it is actually 2 equations but they are going to give you the same rate. So rate, our amount of product produced divided by the time it takes, because obviously if we want to make more product, it is going to take more time. So we do need to be considering the amounts in these. And so then our alternative is our amount of reactant used divided by the time. And again, if you've got more of a reactant, you're going to expect it to take longer. So we do have to take those amounts into effect. So this example is our egg, and this was our popcorn example, where we're thinking about those things. Okay, so thinking about the progression of reactions, we end up having fewer reactants as we progress. So at the start here, this is all reactants, the blue and the red, whereas at the end, this is all products. And so in this reaction, you can see that we start to increase the amount of products. Now, where there are fewer reactants, there can be fewer reactions happening. So how is that going to affect our rate? So pause the video while you have a think about this. So we're going to have a decrease because the less reactant particles there are, the fewer reactions that can be happening. And so because they're less available, our rate of reaction is going to decrease. So if we look at a graph, we can see how it falls into a more horizontal line. So it starts off very steep, and so this is telling us it's happening quickly, it's fast, whereas here we've got a shallow gradient, and therefore it's happening slowly. So our gradient of the graph is decreasing over the reaction, and that is because our rate of reaction is falling, and that's because we have less reactants. So that's what it means by reactant concentration falling, is that we have less reactants in that mixture, and therefore our rate of reaction is going to fall. So can you sketch two graphs, so amount of product over time and your amount of reactant compared to time, and tell us what these gradients of each of these graphs are telling us. So just a reminder how we calculate gradients. You're not asked to calculate it, but just having a think that our gradient is our change in our y over our change in x. You might be familiar with the term rise over run. So thinking about what would happen when you've got your change in y divided by your change in time. Okay, so we can also annotate our graphs. So talking about the gradients that we talked about before, that they are fast when it's steep and slow when it's shallow. And similarly for our amount of reactant. So this one is the one that we didn't talk through before, but do just make sure that you are happy with the fact that in both of these cases we have periods of fast at the beginning and slow at the end where it levels out. So when we get to a horizontal line right at the end, that is when our reaction has stopped because there are no more changes. So we've talked about the fact that we have our gradients being shallow or steep. And so this was the question that I asked a minute ago, was what our gradients are telling us. So they are telling us our rate of reaction, because our change in y is our amount, whether it's of product or reactant, and our change in x is our time. So when we calculate our gradient, when we do our rise over our run, we're doing our amount of product or reactant divided by time. And that, therefore, is our rate of reaction in either of those definitions that we looked at. But you will have noticed that these are curved graphs, they're not straight line graphs. So the rate, and what we've talked about, the rate doesn't change, the rate doesn't stay the same. It changes through the reaction, starting off fast and then getting slower as the reaction progresses. So what we can do though is we can get our gradients at a particular point. And the way we do that is we draw a straight line. So this purple line here is what we call a tangent. So you can see that it follows the gradient at that point there. So we have that straight line where the straight line and the curve have the same gradient, only at that specific point. You can clearly see at the other ends they no longer have the same gradient, but at this point where we've drawn that straight line as a tangent to the curve, they have the same gradient. And so what we can then do is we can calculate the gradient of this tangent line by doing our change in y, our rise, divided by our change in x, the run, making as large a triangle as we can from that tangent line. And that will give us the rate at that specific point. So we also have 3 ways to measure a rate of reaction. So when we're able to do practicals again, we will have a look at these more closely. So this example here, what we have is our reaction happening in a conical flask. Now, marble chips you may have come across before, but you may not have. And marble chips is our calcium carbonate, which is then reacting with an acid. So when we're reacting an acid with a carbonate, we end up producing our salt, calcium chloride, plus water. But because it is a carbonate, we also produce carbon dioxide gas. So in this reaction, and it's not balanced, but that's not important for now, it is our CO2 that is going to indicate to us how quickly this reaction is happening, because this is something that is easily measurable. What we are using here is a gas syringe we can use to collect and measure our volume of gas. And so what we're doing here is we're measuring our amount of product produced. That is how we're going to determine the rate, is we're going to be looking at how much gas has been produced in an amount of time. So in this one, we are looking, and you can see a clear colourless solution with a cross on a piece of paper underneath. So in this reaction, we're going to be producing a solid precipitate, so a solid that's being produced from the reaction, and that is going to stop us from seeing that cross underneath. So in this reaction, we're going to be looking a bit like with the egg, so that we know when it's done, when our amount of product is significant enough to stop us from seeing that cross. And that becomes a point that we can compare the rates of different reactions to. So looking at the time taken in order to produce that significant amount of product. And then in this reaction, but it's the same reaction that was happening down here, but using these scales, we can look at our change in amount of reactant, and using that to calculate our amount of rate. So those 3 ways can be summarised in the following. So increasing the volume of gas produced, So we said we were looking at the product there, measuring the decreasing mass of a reaction mixture. So there we were looking at our reactants being used up, and here that decreasing light passing through the solution, and that was as a result of our products. So thinking then about the units of the rate for method 1 and 2, thinking about what we are collecting and how we can measure those quantities. So pause the video whilst you have a think about those. So our answers there are centimetres cubed per second and grams per second. So centimetre cubed, this is our unit of volume. So this is for our volume of gas. And of course, in both of these cases, our seconds is for our time taken. And then this grams is for our mass of our reaction mixture. Another rate unit, of course, that we could use is moles per second, because this is a quantity for an amount of substance. So you could also come across it like that. And so I'm going to finish up now by looking at 3 graphs. So first graph here, typical of many chemical reactions, drag the letter of each part of the line to the correct description for the progress of the reaction. So pause the video whilst you have a think about these. So first one, which letter represents a reaction that has ended? So we said previously that this is where it has a 0 gradient, and therefore that's going to be position E. Which letter is the reaction where the reaction is fastest? So this is going to be where our gradient is at its steepest, and there, that is the fastest part of the reaction, part A. And then which letter represents where half the reactants have been used up? So if half the reactants have been used up, we are expecting half the products to be produced. So looking between here and here, halfway, I would give you either B or C. More likely that B, but you're looking for where half of the products have been made. Next graph, so looking at an indigestion tablet fizzing and dissolving, comparing the graph of 3 reactions. So again, read the statements and decide which letter goes where. I will give you a moment to decide those. In this reaction, James has broken the tablet up, so he's crushed it up, increasing the surface area and allowing it to react faster. Edward's only put in half the amount, and so we're only expecting half the product. So Edward is going to be C. Lizzie has only added it, so Lizzie's is like the standard to be comparing it to. But for James's to be faster than Lizzie's, we're looking for a steeper gradient, which is going to be A, because we can see here steeper, and therefore Lizzie's standard must be B. Okay, and then this is our final graph. So reading the statements, the graphs have been labelled there, A, B and C. Which one is going to match up to which investigation? So pause the video whilst you have a think about these. Okay, so which experiment used the greatest amount of reactants? This is going to produce the most, and therefore it's going to be A. Which experiment used dilute reactants? So we'll come back to talk about that in a moment. Which experiment might have been performed at a higher temperature? So higher temperature we're giving those particles more energy, and we'll talk about that next lesson, but this is going to increase our reaction rate and therefore is going to be B, because that has the steepest gradient, and therefore C is our one which used dilute reactants. So dilute reactants is going to be having fewer reactant particles, but that is comparing it mainly to 1, but for B to be producing the same, we would have had to have the same amount of reactant particles in that reaction mixture in order to be producing the same. B to a point, because we could just be using less of concentrated substances, and so using something that's concentrated would increase its rate. So putting B in brackets there, C is a definite answer because it's the slowest. B being quite quick, they could be just using a smaller volume of a concentrated substance. So that's all on rate of reaction for today. So hopefully you have completed your worksheet. If you have any questions, please do email me or message me on Teams. Thank you all very much for watching, and see you in the next lesson.